Hello students, today we'll start with the last topic of the Z transform, that is system function of discrete time LTI system. We have already studied for any system, if x of n is input and y of n is output, then if we are giving to a system, the output yn is x of n convolution h of n. Applying the convolution property of the Z transform, we'll be getting y of z is equals to x of z h of z, where yz, xz and hz are the z transform of yn, xn and hn. So we can write h of z as y of z by x of z. The z transform h of z of h of n is referred to as system function or the transfer function of the system. So this is h of z is nothing but the system function or the transfer function. Now h of z can even be written as ratio of the z transform of the output yn and the input x of n. So here it is clearly described in a way that if x of n input is given to a system, the output will be yn, and yn is described as x of n convolution h of n, and in the terms of h of z, x of n will have the z transform x of z, h of n will have the z transform h of z, and yn will have the z transform y of z. This y of z can be written as x of z into h of z, and the h of z is nothing but the transfer function of the system. Now characterization of discrete time LTI system. The first characteristic is the causality property. Now the causality for a causal discrete time LTI system, the condition is h of n should be 0 for n less than 0. That is, h of n should exist only for the n equals to n greater than 0. So this is the condition for causal discrete time LTI system. Now if h of z should be h of n is a right sided sequence, now from this condition we can conclude that h of n is a right sided sequence, and its h of z should be such that the ROC must be mod of z greater than R max. R max is the value of the pole that is at the maximum value of the pole. That is, ROC is the exterior of the circle containing all the poles of h of z in the z plane. So if the system is anti-causal, that is the another case, in that case h of n is 0 for n greater than n equals to 0. H of n is a left-sided sequence. Hence ROC of h of z must be mod of z less than R max. ROC is the interior of the circle containing no poles of h of z in the z plane. Now the second characterization is stability. For a stable system, that is if the discrete time LTI system is BO stable, we already know this condition. It is summation n minus infinity to plus infinity, mod of hn should be less than infinity. That means the summation must be absolutely summable. ROC of the h of z contains the unit circle. This is the important condition for stability, that if we are saying that h of z is stable, in that case the ROC of the h of z must contain a unit circle. Unit circle is a circle of radius 1, mod of z equals to 1. Now considering both the cases together, that is the causality of the system and the stability of the system, if the system is both causal and stable, then all the poles of h of z must lie inside the unit circle. All the poles of h of z must lie inside the unit circle of the z plane, because the ROC is of the form mod of z greater than R max, and since unit circle is included in the ROC, we must have R max less than 1, as according to the condition of the causality, the mod of z is greater than R max. That means the R max is a circle. Here R max is an inner circle where the ROC is the outside of the circle of radius R, and according to the condition of the stability, the unit circle must lie in the ROC. Hence R max should be a lesser value than 1. So this is the condition for a system to be a causal system as well as a stable system, that is R max should be less than 1. That is, the maximum value of the pole should be less than 1. Now systems interconnection. Now if the two system two LTI system with H1 and H2n respectively in cascade. Cascade means representing this particular condition, that is H1n and H2n are connected one after the another. So in that case, if we have to find the overall response H of n is given by H1n convolution H2n, and thus the corresponding system function is related as H of z equals to H1z H2z. The system function will be simply H1z H2z, and the ROC is R1 intersection R2. Now if the two systems are connected in parallel, that is a parallel combination, if we are having first system with H1n as the response of the system and H2n is the response of the another system, then in that case the H of z will be H1z plus H2z, that is the system's function, the combined system's function will be H1z plus H2z, and the ROC is still R1 intersection R2. Now we will see a few of the examples based on this. The first example is if x of n is un and h of n is alpha and un for alpha, which is the value in between 0 to 1, using z transform obtain yn. We have to obtain the value of yn with the help of z transform. Now x1n is un, we already know the z transform of it is z by z minus 1, where mod of z is greater than 1. H of n is alpha and un, and the z transform is h of z by z minus alpha. Now since it's un, mod of alpha should be greater than alpha. Now we know that y of z is x of z into h of z. Now we'll take both the z transforms together, that is the z transform of xn and the z transform of hn, z by z minus 1 into z by z minus alpha. Now in both the cases, as we know, the alpha value is 0 to 1. Hence we have taken the common ROC, which is mod of z greater than 1. Y of z can be written as z square by z minus 1 into z minus alpha. Using partial fraction expansion method, we can write y of z by z as z by z minus 1 into z minus alpha equals to c1 by z minus 1, c2 by z minus alpha, where c1 value can be obtained by this method, and the value is c1 is equals to 1 by 1 minus alpha. Similarly, we can even obtain the value of c2 by putting the value of z equals to alpha in this particular formula. We'll be getting the value of c2 as minus alpha by 1 minus alpha. Now substituting these two values in y of z by z, here we'll be getting this equation. We can write y of z as 1 by 1 minus alpha into z by z minus 1 minus, this is the value of c2, alpha by 1 minus alpha z by z minus alpha, and the ROC is mod of z greater than 1. Now taking the inverse z transform of this yz, will be getting 1 by 1 minus alpha into un. Now this is the inverse z transform of un minus alpha by 1 minus alpha and un. So here we are getting the yn. Now coming to the next example, obtain the impulse response of the system if x of n is un with ROC mod of z greater than 1, and output yn is alpha and un with ROC mod of z greater than alpha. Now here x of n is given to us, which is un, and yn is given to us alpha and un. We already know the z transform of both the sequences. Now what do we want? We know that h of z is yz by xz. Now here we are given with y of z, and we are already having the value of x of z. We can even write it as z by z minus alpha, this is yz, upon z by z minus 1, which is the value of x of z. Now we can write h of z as z minus 1 by z minus alpha, where mod of z is greater than alpha. Now using partial fraction expansion method, we can write h of z by z as z minus 1 by z minus alpha, that is equals to c1 by z plus c2 by z minus alpha, where we can even find the values of c1 and c2 by applying it in the formula of ck. We will be getting the c1 as 1 by alpha and c2 as minus 1 minus alpha by alpha. So h of z is 1 by alpha minus 1 minus alpha by alpha, z by z minus alpha. Mod of z is greater than alpha. Now taking the inverse z transform of h of z, h of n is 1 by alpha into del n. Now here 1 by alpha is a constant term. We know that the inverse, the z transform of del n is just 1. Hence we have taken the inverse z transform of 1 by alpha as 1 by alpha into del n. Minus 1 minus 1 by 1 minus alpha by alpha equals into alpha to the power n un. So this is the h of n which is required. Now taking another example, if the impulse response of the system is given by h of n equals to alpha n un, then we need to check the causality of the system and we need to check the stability of the system. Now h of n is given as alpha n un, and the h of z, the respective h of z would be z by z minus alpha, where mod of z is greater than mod of alpha because it has un attached to it. The ROC of h of z is this. Now from this we can conclude that h of n is 0 for n less than 0, because we from the expression of h of n itself we can find out that h of n is 0 for n less than 0. Hence h of n is a causal sequence and thus the system is a causal system. Now coming to the stability part, we know that mod of alpha is greater than 1. The ROC of h of z does not contain the unit circle if we are taking mod of alpha is greater than 1. Here we don't exactly know the value of alpha. It's not given in the question. So we'll have to assume two cases. If alpha is greater than 1, that means the alpha is a value which is greater than 1. In that case, the ROC of h of z does not contain the unit circle. If alpha is greater than 1, what is the ROC? ROC is mod of z greater than mod of alpha. And if mod of alpha is greater than 1, in that case the ROC will definitely not contain the unit circle, and hence the system will not be a stable system. Now if we are taking mod of alpha less than 1, that is the alpha value is a value which is less than 1, and we already know the ROC is mod of z greater than 1. Now in this case, in the second case, the ROC of h of z will definitely contain the unit circle, and hence the system will be a stable system. Sorry, here I have written not stable. This will be a stable system. This is properly depicted in this particular figure. In the first case, this is a inner circle is a unit circle, the second circle is a circle of radius alpha, and since the ROC is mod of z greater than alpha, and here I have taken the alpha value greater than 1. Here the unit circle is not lying in the ROC, and hence the system is unstable system. In the second case, where I have taken the alpha value which is a lesser value than 1, and the unit circle is lying in the ROC. ROC is mod of z greater than mod of alpha, and the unit circle is lying in the region of convergence, and hence the second condition is a stable system. So students, just make the correction here. This will be a stable system. The second case will be a stable system. Here by mistake I have written it as not stable. Just make it a correction. Now the next example, a causal discrete time LTI system is described by this one: yn minus 3 by 4 yn minus 1 plus 1 by 8 yn minus 2 equals to xn, where xn and yn are the input and output of the system. Now we need to determine the system function h of z, and we need to find the impulse function, impulse response h of n of the system, and the step response h of n of the system again. So for finding the transfer function, we are writing the equation which is given to us, that is the system is given as y of n minus 3 by 4 yn minus 1 plus 1 by 8 yn minus 2 equals to xn. Now we'll take the z transform, will be obtaining yn, the z transform will be yz directly, minus 3 by 4. Now here we are given with yn minus 1 minus 3 by 4 yn minus 1, taking the inverse taking the z transform of it, this becomes z minus 1 y of z, that is due to the property of time shifting, this becomes z minus 1 yz, and 1 plus 1 by 8 z minus 2, here y of n minus 2, this is z to the power minus 2 y of z equals to x of z. So here we are applying the time shifting property and we'll be getting this particular z transform equation. Now we can even write it as taking yz common to all, 1 minus 3 by 4 z to the power minus 1 plus 1 by 8 z to the power minus 2 equals to x of z. Taking y of z by xz, this is what we'll be getting 1 by 1 minus 3 by 4 z to the power minus 1 plus 1 by 8 z to the power minus 2. If we are writing it in this form, that is multiplying z square in the numerator and denominator, will be getting z square by z square minus 3 by 4z plus 1 by 8. Hence y of z by x of z is nothing but h of z. H of z is the transfer function of the system. This can be written as z square by z minus 1 by 2 into z minus 1 by 4. Now this particular denominator can be further factorized as z minus 1 by 2 into z minus 1 by 4, where ROC is mod of z greater than 1 by 2. Now this is what is the A part of the question. Now coming to the B part, we want to find the h of n. Using partial fraction expansion, this can be written as h of z by z equals to z by z minus 1 by 2 z minus 1 by 4 equals to c1 by z minus 1 by 2 plus c2 by z minus 1 by 4, where we can find the values of c1 and c2, and we'll be getting c1 as 2 and c2 as minus 2. Substituting these values, we'll be getting h of z as 2 into z by z minus 1 by 2 minus z by z minus 1 by 4, since the value of c1 is 2 and c2 is minus 1. So taking the inverse z transform of it, 2 into z minus z by z minus 1 by 2 is 1 by 2 to the power n un minus this one, that is z by z minus 1 by 4, can be written as minus 1 by 4 to the power n un. So this is what is the equation for h of n. Now we want to find the step response, that is the C part of it is to obtain the step response of the system. Now if x of n is a un, x of n is a unit step function, the response obtained would be definitely will be a step response of the system. So we have to take x of n as un and x of z would be z by z minus 1. Now taking y of z is nothing but x of z into h of z. So we have this h of z here, as we have already obtained h of z from the previous part, that is from the A part. This was our h of z, z square by z minus 1 into z minus 1 by 4. We'll just multiply it with x of z. So x of z is z by z minus 1. So this becomes z cube by z minus 1 into z minus 1 by 2 into z minus 1 by 4, and the ROC is mod of z greater than 1. Now again applying the partial fraction expansion, we can write y of z by z as z square by z minus 1, z minus 1 by 2, z minus 1 by 4, and this can further be written in three parts, that is c1 by z minus 1 plus c2 by z minus 1 by 2 plus c3 by z minus 1 by 4. Now we can obtain all the three values of c's, c1, c2 and c3. C1 is 8 by 3, c2 is minus 2 and c3 is 1 by 3. Now substituting these values, we'll be getting y of z as 8 by 3 into z by z minus 1 minus 2 by minus 2 into z by z minus 1 by 2 plus 1 by 3 into z by z minus 1 by 4, where mod of z is greater than 1. Now taking the inverse z transform, we'll be getting yz is nothing but, taking the inverse z transform, we'll be getting yn is nothing but the step response, because the input that we have taken here is un. Hence the step response of the system is 8 by 3 un minus 2 1 by 2 to the power n un plus 1 by 3 1 by 4 to the power n un. Now this was the last question. Now the last example of this unit is, consider the discrete time system shown here. For what value of k the system will be a Peebo stable system. Now this is the input which is given to a summation, and from here we are directly giving to a z inverse block, that is to a time delay block. From here we are giving to a multiplier block. This multiplier block is having a value k by 2 and this multiplier block is having a value k by 3. Now from here it is given to a summation block, and from there the output is taken. Now from the figure, this is the figure given to us, we can write the expression as, here we are considering as qn. Let Qn is the first intermediate that we are taking, and if it is given to a time delay block, it will be q of n minus 1. The output from this block will be a qn minus 1. If here it is qn, here it will definitely be qn minus 1. So that is what we have written here. Qn is equals to, if I'm taking qn here, it is the summation of xn plus k by 2 qn minus 1, that is xn plus k by 2 qn minus 1. Similarly, we can even write yn. Yn is qn coming from here and k by 3 qn minus 1 coming from here. So these are the two equations that we can write from the figure given to us. Now taking the z transform of the above equation, qn can be written as qz, y of x of n is x of z plus k by 2. Here it is qn minus 1, that can be written as z to the power minus 1 q of z, and this can further be written as 1 minus, taking this particular term in the left side, 1 minus k by 2 z to the power minus 1 into qz equals to x of z. Similarly, for the second equation, we can write y of n as y of z and q of n as q of z, and k by 3 z to the power minus 1 qz for qn minus 1. So this is the equation, the second for the second equation. Now this can be further written as 1 plus k by 3 z to the power minus 1 into qz equals to yz. We already know that h of z is yz by xz. Now we can write it in this form, h of z as yz by xz, taking yz by xz, that is 1 plus k by 3 z to the power minus 1 by 1 minus k by 2 z to the power minus 1. Further we can write it as z plus k by 3 z minus k by 2. Now mod of z is greater than mod of k by 2, that is h of z is z plus k by 3 z minus k by 2, and the ROC is mod of z greater than mod of k by 2. So for the system to be a Bibo stable system, if this is the ROC, that is mod of z is greater than mod of k by 2, for the system to be Bibo stable system, the ROC must contain the unit circle. This is the only condition for the system to be a stable system, that ROC must contain the unit circle. Hence the system is stable only if mod of k by 2 is less than 1. This is the mod of k by 2, ROC is greater than mod of k by 2. If mod of k by 2 is less than 1, then only the ROC will contain a unit circle, that is the mod of k should be less than 2. So this is the condition of k, that mod of k should be less than 2, for which the system will be a Bibo stable system. That's all students, all the best and do well in the exam.